We have already derived a number of expressions on this rather busy slide, but now let's go ahead and solve a few examples, two fundamental and one little bit more complicated and general, in order to demonstrate the ideas that are stated here. So I'm going to refer back to this slide, to the especially two sets of equations, blue and red, in order to solve these problems. Now, I'll just put this over here and let me describe you these two problems. The first problem is going to be a simple uniaxial tension problem. So this is a rod, and the coordinate system here is x, y, and we are applying a tensile stress of value 100 MPa. And the second problem is going to be a square. If you like, we are at a point in the structure where we observe, again, with respect to our usual xy coordinate system, shear stresses of value 10 MPa. So in this case, the normal stress obviously is sigma y. All right. And the question in both cases is find the principal stresses and the orientations, both normal and shear values. So let's start first with the problem on the left. So on the left, we have sigma x equals 0. So if I were to translate this problem into a so I could concentrate at a certain point in the structure, in this beam, and at that point I could write the state of stress on an element as sigma x equals 0. It's not there. This is 100 MPa, and there is no shear stress. Goes without saying, always in the opposing faces there are also similar stresses. I'm not drawing those in general. Okay, so what we would like to do is now find the principal stresses associated with these problems. Now, the first one is this one, and here I will first refer back to these equations, and I'll try to figure out what the principal, let's say, directions and the values are. So first of all, I can observe that sigma x is 0, sigma y is non-zero, but in particular tau xy is 0, and therefore if I look here, tau xy 0 delivering a overall result of 0 so for 2 tangent theta n, twice theta n, and therefore the observation is that tangent 2 theta n is 0, and hence theta n in this particular case is equal to 0. Well, that's no surprise because the loading is already in a state that is a principal that is equivalent to a principal state of loading. Well, how do I know that? Well, we have to go back and remember what is special to the principal normal directions. What is special is that on those on a picture that is associated with those principal normal directions, there is no shear stress. So whenever I see a certain orientation on which there are no shear stresses, I know that's directly the principal normal orientations. And therefore, this is already a principal normal orientation, and hence theta n is equal to 0. So I've concluded that this is already equal to the one direction, this is already equal to the two direction. So if I associate sigma 1 with the new value of x after rotation, as I've sort of hinted here, so x rotates to x prime, and when x prime is 1, it's sigma 1, y rotates to y prime, and when y prime is equal to 2, sigma y prime is sigma 2. So here, as a result of that, sigma 1 is equal to 0, sigma 2 is equal to 100. Always in MPa. I'm not going to write it explicitly. So therefore, these are the principal normal stresses. Notice again that sometimes one prefers to call the maximum one sigma 1, the smallest one sigma 2, but I'm just associating 1 with the rotated value of x, 2 with the rotated value of y. So then the next question to ask would be, what is theta s? Now, I don't have to do really a calculation. I know that theta s is actually plus minus 45 degrees with respect to theta n. We have already found out that result. So that's equal to plus minus theta s or vice versa. So theta is plus minus 45 degrees. And there will be two values of tau 3. It will be either plus or minus a certain quantity. So let's write it as a single value with a plus minus. So here I will have a tau 3 equals, well, I can go back now to this equation, right? And tau 3 occurs on a plane of plus minus 45. Here I can also easily see that because tau xy is 0 in this problem, and therefore in order to have, well, division by 0 delivers undefined, that means 2 theta is plus minus 90, and therefore theta is plus minus 45. That's another way to conclude that result that that we have written over here. So now so if I now go and try to calculate the value of tau 3, well, it's going to be sigma x, which is 0, sigma y over 2 squared, and then square root. Tau xy is already 0, so it's going to be plus minus sigma y absolute value over 2. Notice it's absolute value over 2, so plus minus sigma y absolute value over 2. So whether plus or minus doesn't really matter because there's already a plus and minus here, but I'll keep that absolute value sign, and in this case, therefore, it is equal to 50 MPa. So it is equal to plus minus 50. All right, good. So the principal normal direction, that's the blue direction, it is that direction. It's already a principal plane, so I'm drawing the line associated with 1. And then there are principal directions associated with theta s, which is plus or minus 45. So either that or that orientation. Both of them are orientations along which the shear stress is a maximum. In one case, it's a plus. In the other case, it's a minus. So that's the first problem. Then we can go to the next problem. And in the next problem, we have, so let's draw a line here. In the second problem, we have a pure shear scenario. And I am interested in the, again, the same questions. What are the principal, normal, and shear directions? So here I can immediately start with the value of theta s. Now, what is special about the value of theta s? Well, what's special is, again, if I go back to this picture, actually, what's special is that the normal stresses are equal. This is one way from which you can deduce the definition or the observation that this is a direction, set of directions associated with the principal shear stress. So in this case, sigma x and sigma y are both equal to 0, and hence I can conclude that this is already a picture that is associated with the principal shear stresses. And therefore, there will be two values, tau 3, which are actually plus and minus 10 MPa. Now, let's come back to what this plus and minus refers to. But before we do that, I will go back to the theta and setting. So now if I go back to the theta and setting, and by the way, we could have deduced that theta is equal to 0 also by looking at this equation over here. Okay, and in that equation, what I observe is that sigma x and y are both 0. So this is 0 divided by something, and therefore theta s must be equal to 0, right? Okay. So now I can go back to this picture and try to determine now the value of theta n by referring to these equations. Now, tau xy is non-zero, sigma x and y are both 0, and therefore theta n must be, because it's undefined, tangent to theta n is undefined. Theta n is again plus minus 45. I know that if theta is 0, theta n is plus minus 45. I could have already deduced it from there. And from these, I can, these are degrees, I can calculate sigma 1 and sigma 2. Okay, and of course, what I am going to find directly from those equations? Well, x and y are originally 0, so it's tau xy square root, so in other words it's already 10 plus minus 10. So sigma 1 is going to be a plus, sigma 2 is going to be a minus. MPa again, all right? So that's the solution to my simple problem. So these are cases of fundamental interest, and the reason is that this is a case where I have pure uniaxial loading, and which says that, first of all, if the material were brittle, that means that we'll see it's sensitive to the plane on which the stress, maximum normal stress, eventually reaches some critical value. That's this blue line here. That's already the direction perpendicular to the direction of loading. And I've already given you an example. What we expect with a brittle material like glass is that it fails like this along the blue line. And on the other hand, a material like metal fails across one of these red lines usually, or those lines are indicative of its failure regions. And that is because metals are sensitive to maximum shear, okay? Not in absolute terms, we will state rigorously what the criteria are, but we see now that the maximum shear occurs on planes that are oriented at certain angles close to, well, in this idealization, plus minus 45 with respect to the axis of loading. So now you see, we are able to deduce with the tools that we have the planes on which maximum normal or maximum shear stress occurs. And ultimately, that's going to help us with the decision of whether failure is about to happen or not. So finally, let's come back to this issue of a plus minus in the principal shear stress. So now, if I had rotated this thing to an arbitrary picture, I would have tau xy prime at a given rotation and normal stresses as well. But I'll pick a very special rotation for my axes, going from left to right. It's still the same scenario. Notice, remember, we're always at the same point. I'm just choosing a different orientation, and I'm going to pick an orientation that looks like this. So I'm going to rotate through 90 degrees such that this now is x prime and that now is y prime, okay? So remember, according to my orientation, this one, the normal stress is going to be sigma x prime. The shear stress is on the plane with x prime in the y prime direction. It is tau xy prime. And on this plane as well, there's going to be the same thing of the same value, and goes without saying I have the same things here. But now you compare that picture and that picture. Of course, in general, there will be a sigma x prime and y prime, but they are 0 because this picture and that picture are actually exactly equivalent. Now, the state of stress is the same. I'm just rotating the coordinates, but also it's the same picture. I mean, the orientations are still the same. It's just that these axes have been flipped, okay? So here, tau xy is plus, okay? So in other words, there is already a principal shear stress, okay? That is plus minus, right? That is equal to plus 10 MPa. But if I rotate through 90 degrees, then I get a shear stress, which is supposed to be equal to that picture. And therefore, on that picture, tau xy prime is supposed to be equal to minus 10 MPa. Why? Because the two pictures are entirely equivalent, also in terms of orientation. And for this to be equal to that, for this given default choice of direction, which aligns with these axes, the value must be negative, so that actually it is in the other direction, just like here. So that's where the minus comes from. So there is a principal direction, theta s equals 0, but remember, there is another principal direction always that is at an angle of plus minus 90 degrees with respect to that direction, right? So that is, for instance, plus 90 degrees, or I could have rotated by minus 90 degrees, still I would get the same picture. That is the other corresponding principal picture. It's the same picture, but it's just that the principal shear stress now is not positive, but it's negative. From now on, whenever we talk about the principal shear stress, we will understand exactly the same thing occurring on the background, and therefore I'll just give you the positive value. The positive value is sufficient. We always remember that there is a negative value. Now, these were rather straightforward examples. Now, what I will do is I will go ahead and solve actually a slightly more complicated problem. And the slightly more complicated problem is described by a scenario where we have a state of stress that is described with respect to our original coordinate system, and it is equal to the following picture. So remember again, we're at a certain, right? I should emphasize that at this stage again and again. We have a certain structure. The structure is subjected to certain loads. Not all of them have to be non-zero, but suppose these are the general things that we consider in ME 231. Then we look at a point on the structure, and that's that point we're looking at. And at that point, with respect to our conventional axes, which might, for instance, x might align with this direction, I have the following stresses, right? So I'm drawing something very general, not necessarily corresponding to that picture. I'm just motivating the fact that what we're looking at is not a structure on its own, but actually a point somewhere along the structure as we load it. So the loading is such that we have a normal stress 80, another normal stress 40, and then shear stresses which are equal to 30. Goes without saying again, we have the same things on the other surfaces. So what we are asked to find again is find the principal stresses, sigma 1, sigma 2, tau 3, and associated with those what the orientations theta n and theta s are. Okay. So let's go ahead and actually do the calculations now. Now, we're going to use actually the equations that we have up here. And this I leave to you to a large extent. What you will find are two stresses. Okay. So if you go ahead and plug these values in there, the only thing you have to be careful about is always the values. Now, the arrows indicate the direction, or ultimately the sign, and the absolute values are given in terms of the magnitude here, over here, right? So all the directions are the default directions. So here, this must be sigma x, and it is plus because it's in the default direction. These must be tau xy, already plus, and this must be sigma y. So all the stress components are actually positive in this case. And so I will go ahead and calculate sigma 1 from the equation that we have. So we have sigma 1, in fact 2, is equal to x plus y, so 80 plus 40 divided by 2 plus minus square root. Again, 80 minus 40 divided by 2 squared plus 30 squared. So that's going to give you two values. You'll obtain sigma 1 equals 96.05 MPa. Everything is in MPa, I'm not denoting it. And sigma 2 is equal to 23.95. Okay, all right, so that takes care of the principal normal stresses. Well, how about the orientation? Well, you can go ahead and use that equation by plugging in the correct values. You will find that tangent 2 theta n is equal to, or 2 theta n is equal to tangent inverse of 2 tau xy, which is 60 divided by sigma x minus y, which is 40. Okay, so this is 0.9828 radians roughly. Remember, the result is usually radians. You want to convert that if you want to degrees 1. 2, remember that there's always a factor of 2 within the angle that you're trying to calculate. Tangent 2 theta n is equal to that quantity. So as a result, you can calculate that theta n is equal to 56.80 56.3 degrees approximately. Okay, good. Of course, plus minus pi over 2 is also another solution, but I understand that this is already descriptive of what is going on, because plus minus pi over 2 is just going to send me to the other plane associated with the other principal direction. Okay, so there are two directions, sigma 1 and 2. So if 1 is associated with that direction, 2 is associated with plus minus that direction, plus minus 90 that value. So now there is tau 3, which is actually exactly that value. So it's going to be, let's still write plus minus 36.05. And PA goes without saying. And here, theta s is not something I need to again calculate. If you want, you can do so. But it is directly that plus or minus 45. I'm just going to take the plus value, 45 degrees, which therefore is 73.15 degrees. The other one will send me to the principal stress with the other sign. If one is plus, the other one is minus, but really they are the same thing. Okay, so that is the solution of our problem. Okay, now it is, of course, a little bit discomforting that in order to answer questions, for instance, in this case, well, if the structure is sensitive to maximum shear stress, where does it occur and what's the value? And by looking at that value, I can compare it against some material property and decide if there is failure or not, right? Certainly, this value is larger than that. I cannot decide failure accurately based on the value that I observe in the original picture. I have to search for the maximum value. But that search requires a number of equations, right? And those equations are over here, and they're quite hard to remember. And so what we will do next is we are going to put these equations in actually a form that is a lot easier to remember and practically very useful. Okay, so that's our next goal.